Welcome back, everybody. And this week we're going to go back to more traditional quantum mechanics. That is, quantum mechanics described in terms of the Schrödinger equation. And today I'm going to solve the Schrödinger equation on a number of very important examples, where I will show you how quantum potentials can capture quantum particles that results in so-called bound states. So even though the solutions that we're going to see, the examples we're going to see, are rather elementary from the quantum mechanical point of view, well, otherwise they will require some thinking. So these examples are going to give us insight into some rather complicated and fascinating problems, such as, for instance, theory of superconductivity. So in the end of the lecture today, we're going to discuss how our solutions are relevant to the key phenomenon that is responsible for superconductivity, that is so-called Cooper pairing. But before we get to this point, we need to go over the basics. And so let me start first with the problem of electron in a box that I will define in a second. But even before that, let me just talk about what kinds of problems we want to we can possibly study with the Schrödinger equation. So here's the canonical Schrödinger equation. We have seen it already many times. It's a time-dependent Schrödinger equation, as we will see later today. So actually, if the potential does not depend on time, there is really no need to study the time-dependent Schrödinger equation. So we'll see it can be transformed into an eigenvalue problem for the Hamiltonian that we will actually solve. And in any case, so this first term in the single particle mechanics anyways, so this first term in this Hamiltonian is just the kinetic energy. So there is essentially, it's non-negotiable term. And the second term is something which is sort of problem dependent, which determines the potential in which our quantum particle moves. So amazingly, the variety of all possible problems in single particle quantum mechanics are contained in this equation in a compact way. And they differ simply by the choice of V of r. But this compactness of basically quantum mechanics is a bit deceptive, because it can give you the impression that you can just solve all possible quantum mechanical problems in one go just by solving this equation. Well, this equation is a very rich equation, and depending on the choice of V of r, of the potential in which the particle moves, we can get completely different physical situations, and understanding these physical situations would require dramatically different mathematical approaches too. However, very roughly what we can do, we can classify our quantum potential by putting it in one of two categories of either an attractive or a repulsive potential, which in the context of quantum physics are called, the former are called potential wells and the latter are called potential barriers. So here let me present a, well, sort of simple illustration of what a typical potential well looks like. So this is V of x. It's in 1D quantum mechanics, and this is a 1D coordinate, and a potential barrier would look sort of opposite to it. It would look like a hill. And today we're going to focus our attention on the physics of quantum potential wells. So, and basically to give you sort of the result right from the outset, and most of you probably already know this, in potential wells, we're going to see that the available energy levels for the particle to occupy with the negative energy are going to be quantized. That is, the particle wouldn't be able to have any arbitrary energy, just like in classical physics, where we could assign any energy. We could put, let's say, a ball at any level and let it oscillate between the turning points. In quantum mechanics, let's say if you put an electron in a potential well with this landscape, we cannot assign it an arbitrary energy. So the available energies are going to be quantized. And finding these quantized energy levels is one of the sort of canonical problems that we're going to solve. But this business about finding the quantized energy levels in an arbitrary quantum well is in principle rather complicated technically. And the complexity of this sort of exercise much depends on the particular form of the potential we're studying. However, to see the appearance of these quantum levels in general, we can focus on the simplest examples of V of x, and that's what we're going to do now. And perhaps the very simplest example is a potential which has so-called hard wall boundaries, which implies the following. So it basically means a potential where beyond certain points, let's say x equals 0 and x equals L, so the value of the potential V of x is equal to infinity. So there is no way the particle can move beyond these points. These are infinite walls. And in between these two points, the value of the potential is exactly equal to 0. So which means that the particle is sort of free to move between these two walls, but it cannot go outside. And this is what is known as a problem of an electron in a box. So as you probably can guess, the solution of this problem that we're going to complete in the remainder of this segment is going to involve certain energy levels which are going to form a discrete series. So it turns out that to understand the phenomenon of quantization, one doesn't really need quantum mechanics at all. The quantization occurs in classical physics all over the place. And so here, for instance, we have an example of a very familiar object, a guitar, which relies on quantization in some sense of the wavelengths and frequencies available in its oscillating strings. So here we have strings sort of which are free to oscillate between 2 points where they're pinned down, and those 2 points in some sense correspond to the hard wall boundaries in the corresponding quantum mechanical problem that we're going to study a little later. And the available wavelengths much depend on the distance between these points, between these hard walls, let's call it L, and the corresponding frequencies are related to the available wavelengths via the speed of sound. Let us now think about what is the longest possible wavelength that we can induce in a finite string. So these are basically our hard walls again. So this is our 0 and this is our L. And the hard walls in this context essentially mean that the strings cannot oscillate here. So the displacement, let's call it U, from this horizontal axis is exactly 0 at x equals 0 and x equals L. In other words, so we must have nodes at these endpoints. And the longest possible wavelength that achieves that is lambda equals 2L. And this is sort of the fundamental oscillation that we can, the longest possible wavelength that we can induce in this string. Because if we try to make the wavelength even longer, it would imply essentially that we would have either no node in this point or no node in this point, and this will violate our boundary condition. But there are, of course, many more wavelengths that are possible that would satisfy the proper boundary conditions. And we can achieve, we can sort of find these additional wavelengths, or higher harmonics, as they're called, by putting additional nodes in between these endpoints. And so, for instance, this example gives us a wavelength which is exactly equal to the L, to the distance between the endpoints. And we can continue this procedure and generate many more wavelengths. And these wavelengths are going to follow this quantization rule, if you want. With the corresponding solution, well, if you look at the snapshot of an oscillating string at a certain time, so the solution is simply going to be given by the sign, well, some amplitude which is not really important, sine of 2 pi x over lambda sub n. So, and of course, if x is equal to 0, we're going to have the boundary, we're going to satisfy the boundary condition at x equals 0. And if x is going to be equal to L, this quantization rule is going to enforce the other boundary conditions, namely that the displacement vanishes at x equals L, or we have a node here. Now, if we look at the corresponding quantum mechanical problem, so it essentially is very similar to the problem of this oscillating string, with the only difference being that instead of putting an elastic string in between the 2 points, we put an electron wave in between these 2 points. But the wavelengths that are available for the electron, so the electron cannot really move beyond these hard walls, right? Or the probability of finding the electron there is equal to 0. Therefore, we must demand that, well, the probability psi squared of at x equals 0 and L is identically equal to 0, okay? So, or in other words, psi itself is equal to 0, and this is much similar to having a node at the endpoints of this string. So if we solve this problem for the electron, well, which will involve in this case actually solving the Schrödinger equation, we're gonna find exactly the same wavelength, and the wave function is actually going to look exactly the same as the displacement of the string. So there's absolutely no difference. I just copy pasted exactly the same equations. So only replacing u sub n, which is the displacement, by psi of n, which is the wave function of the electron. So this shows you that actually there is a lot of analogy in quantization of electron wavelengths and quantization of wavelength of classical objects, elastic objects. So the only difference, and an important difference here, would be in how the frequency or the energy in the case of electron scale with the wavelength. So here we discussed that the frequency of the oscillation, which by the way determines the sound that we actually hear, scales linearly with the wavelength. On the other hand, we know that the energy of a quantum particle, kinetic energy essentially of a free particle moving in between these 2 points, is going to be p squared over 2m. And if we recall the de Broglie relation between the momentum and the wavelength, which is 2 pi h bar over lambda is equal to p, so then we can readily combine these two results, the quantization of the wavelength and the scaling of the energy, to get the quantization of energy. So if we put everything together, this quantization rule and the de Broglie relation, we're going to get the quantized energy levels E sub n, where n is a positive integer, equal to pi squared h squared n squared divided by the L squared, the distance here. This corresponds to the momentum squared, times 1 over twice the mass. So, and notice that interestingly we solved the Schrödinger equation without even writing it down. The only thing we used is basically was the boundary conditions and some analogy with classical physics along with the de Broglie relation. But of course, one can solve it formally, and we're going to show later how it works. So, sadly, one cannot always solve the Schrödinger equation in such a simplistic way without writing it down. So, and to understand why it happens, we can again use this guitar sort of string analogy. So, if we push down on the string, so we effectively shorten the distance between these endpoints and the effective endpoints that we enforce here, and by doing so, we of course change the fundamental wavelength and the quantization of the wavelength and the frequencies. This sort of results in different sounds that we produce this way. But if we push not very hard, but if we just touch the string here, so this creates, instead of an infinite wall, sort of the impenetrable wall for the string to propagate beyond this point, it creates a finite barrier. And to solve the wave equation for the string, the classical wave equation in the presence of such a small perturbation, is actually more complicated than solving this equation for two hard walls. And likewise, we're going to see actually that the problem of a quantum mechanical particle, when instead of the hard walls we have, let's say, finite barrier here, is slightly more complicated, and it requires actually serious mathematical calculations and solving the actual Schrödinger equation, which is a differential equation. We're going to discuss it in the following segment.